So, you want to get into machine learning, but where do you even start? There's so many models, so many names. How do you pick the right one? Well, that's exactly what we're going to figure out today. Let's jump in. Look, if you've ever Googled machine learning, you've probably seen it. Just this wall of jargon, right? Regression, classification, neural networks. It's enough to make your head spin. It can honestly feel like you're trying to learn a whole new language. But I promise it's not as scary as it looks. We're going to make sense of it all.
Okay, here's the best way to think about this. Forget all the complicated algorithms for a second. Instead, picture a toolbox. That's it. You've got a specific job you need to do, and inside this box are different tools, each one perfect for a particular task. I mean, you wouldn't use a saw to hammer a nail, right? It's the exact same idea here.
To get started, let's focus on the 3 big jobs you'll run into most of the time. Seriously, almost everything you'll do in machine learning is some version of one of these 3 things.
First up, what if your job is to predict a number? Not a yes or no answer, not a category, but a specific, concrete value. Like, how much is that house going to sell for? Or what's the stock price going to be next Tuesday? In the world of machine learning, the tool you'd reach for is called regression. That's the fancy name. But whenever you hear that word, I just want you to think one thing: predicting a number. Simple as that. It's all about finding patterns in your data to guess a future number.
And you see this everywhere. Trying to figure out a house's price based on its size and neighborhood? Yep, that's a regression model. Forecasting your company's sales for the next quarter? That's regression too. It is absolutely one of the most fundamental tools you'll have in your box.
Okay, let's grab our next tool. What if you don't need a number? You need a label. The job isn't to predict how much, but which kind. You're basically trying to sort a pile of stuff into different buckets.
The tool for this job is called classification. It does exactly what it sounds like. It assigns a class or a category to something. Is this email spam or not spam? Is this photo a cat or a dog? It's your digital sorting hat, basically. And just think about how often you interact with this. That spam filter in your email, that's classification. When a company wants to know if a customer review is positive or negative, also classification. It's even what helps your bank flag a transaction as potentially fraudulent. Super, super useful.
All right, on to our 3rd and final core job. Now this one's a little different. What if you start with nothing? No labels, no categories. You just have a big, messy pile of data, and you want a machine to go in and find the natural patterns for you.
For this kind of detective work, you need a clustering tool. They call this unsupervised learning because you're not supervising the outcome with any answers. You're just handing the computer the data and saying, hey, go find the groups for me. It's an amazing way to discover customer segments you didn't even know existed.
But you know, just like you have Phillips head and flathead screwdrivers, there are different clustering tools. You have to pick the right one for your data. Some tools are awesome at finding nice round groups. Others are built to find weird, long, sneaky patterns, or to separate the real groups from just random noise. The trick is to match your tool to the shape of the patterns you're looking for.
So we've got our 3 main tools. But what if you have a really tough job and just one tool isn't cutting it? Well, you do what anyone would do. You call in a team. And that brings us to what are called ensemble methods.
The idea here is actually pretty genius in its simplicity. Why would you trust the opinion of just one model when you can ask a whole bunch of them and combine their answers? It's literally the wisdom of the crowd applied to algorithms. And guess what? It almost always gives you a better, more reliable result.
Now, there are 2 main ways you can build these teams. The first is called bagging. This is like asking 100 different experts the same question, but you give each one a slightly different piece of the evidence. Then they all vote on the final answer. The other way is called boosting. This is more like a relay race. The first model makes a guess. The second one looks at its mistakes and tries to fix them. The third learns from the second one's mistakes, and so on, getting better with each step.
This table really helps clear things up. But to get it, we need to know 2 key terms: bias and variance. So, think of an archer. If the archer has high bias, it means all their arrows are hitting the same spot, but it's the wrong spot. It's a consistent error. If the archer has high variance, their arrows are just all over the place. They're unpredictable. So, with that in mind, look at bagging. Its goal is to decrease variance. It averages out all those random, all-over-the-place shots to find the center. Boosting, on the other hand, is all about decreasing bias. Each model in the sequence tries to correct that consistent error, inching closer and closer to the bullseye. Okay, we've gone through the hand tools, we've talked about teamwork. Now it's time to open up the special case and break out the heavy machinery, the power tools. Let's talk about neural networks. Now, before you get intimidated by the name, check out this quote. It really brings the idea down to earth. A single artificial neuron isn't some magical brain cell. It's really just a tiny calculator that takes in some information, does a quick math problem, and if the answer is important enough, it passes a signal along. So if one of those neurons is a tiny calculator, a neural network is what happens when you link together thousands or even millions of them in layers. When they all work together, this massive web of calculators can learn incredibly complicated patterns. This is the magic behind stuff you use every day, like your phone's voice assistant or self-driving cars.
But, and this is a really big but, all of that incredible power comes at a price. Because these networks are so incredibly complex with millions of tiny connections, they often get called a black box. They can give you an amazingly accurate answer, but good luck trying to figure out exactly why it gave you that answer.
And this chart shows that trade-off perfectly. See, way over on one side, you've got a simple tool like linear regression. It might not be the most powerful, but it's super easy to understand and explain. We call that high interpretability. Then, way on the other side, you've got a neural network. It's got mind-blowing accuracy, but its interpretability, it's really, really low.
And this might be the most important lesson of all. Choosing the right tool isn't always about grabbing the biggest, most powerful one. It's a strategic choice. I mean, think about it. If you're building a model to approve or deny loans, or to help a doctor with a diagnosis, you don't just need the right answer. You absolutely need to be able to explain why you got that answer.
So there you have it. We've laid out the whole toolbox. You've got tools for predicting numbers, for sorting things, and for finding hidden groups. You know how to team them up for extra power, and you've even peeked at the heavy machinery with neural networks. So the question isn't, what do all these tools do anymore? The real question is, what problem are you going to solve?